can you possibly put penetrating electrodes into the retina, right, which has the consistency of wet tissue paper? It just seemed impractical. And it took years, but let me show you what we've done. So here you see an OCT, an old OCT. Here's the electrode array against the retina. You can see it's completely conformally aligned. And each of these black areas represent posts that are aligned within the retina. That's a very low power view, just to show you that we were able to do it over a very wide area. Here, let's look in more detail with histology. So here you can see the electrode array, dark down here, with the post going into the retina, all nicely aligned at the junction of the ganglion cell layer and the inner plexiform layer. This is the area we would like to stimulate. And more importantly, and this is the picture that I'm most proud of after 30 years of research, this one picture. So here you see two different stains. Here's the electrode, the substrate for the electrode array. This is a single post. The blue stain, this is the epiretinal surface, by the way. The blue stain shows neurons. The green stain, synaptophysin, MAB30, shows neuronal synapses. So here we have the tip of the electrode array in contact with neuronal synapses and surrounded by a small cluster of retinal neurons. We're not stimulating from the surface. We're actually going to be stimulating from within the retina, which has several significant advantages. It has been shown conclusively through retinal physiology that our stimulation thresholds should be a tiny fraction of what they would be on the surface of the retina. Secondly, because the stimulation thresholds are a lot smaller, it'll be safer to deliver this stimulation, and the electrodes themselves would be likely to survive longer because there's less electricity going through the metal. Most importantly, we will presumably be able to stimulate small clusters of nerve cells that should make the percepts more detailed compared to if we were stimulating with a large electrode at the side of the retina. These are all theoretical advantages. It's going to be our job to demonstrate this with human implants, but we do think this matters. You should be asking yourself this question. Okay, so you can put 300 plus electrodes into the retina at the level that you want. That sounds good, but how much damage are you doing? And here you see two stains. One, the green stain, is the GFAP stain, which stains astrocytes, and the red stain, CD45, stains activated microglia. And what you can see very clearly is that the GFAP staining is typical for any kind of eye surgery that you have, any kind of retinal surgery. You do get upregulation of GFAP across the entire retina, so this is not unexpected. But perhaps more importantly, there are some activated microglia, but almost no reaction at the tip of the electrode array. This surprises me, but it seems to be true. And it may have something to do with the materials properties. Remember, this is metal up here, an insulator here. But at the metal surface, there's essentially no gliosis, or at least not enough gliosis that one would fear it interfering with the electrical stimulation. Now here at KKESH, you've implanted 12 Argus 2 devices, which I wanted to show you this picture. Again, I give Second Sight and Mark Ramayan a lot of credit for what they've done. They have advanced the field. And I think the fact that their patients, that they've demonstrated safety, first off, and that their patients have had some benefit helps us. So I'm appreciative of that. Their device has 60 relatively large electrodes, which you can see here. These are 220 micron diameter electrodes. And these are not microfabricated. So this is silicone. They're embedded in silicone. And here they're tacked to the retinal surface. Right? That's the difference. This is epiretinal, ours subretinal. So we're using a completely microfabricated technology to use smaller electrodes. Okay, now one of the other important strategic advantages is that I have been blessed to be the medical advisor to a company called Magic Leap. This is a vibrant startup company in Florida in the United States. It has been enormously successful in raising money for its work. It's raised almost $2.5 billion as a startup company. Just 4 weeks ago or so, 3 weeks ago, the Saudi Public Investment Fund invested $400 million in Magic Leap. So why, right? Because they have developed an augmented reality technology that is stunning. And the CEO of that company understood that it has medical benefits. And part of the reason I was blessed by coming into the company is to try to help think of how it could be used to help blind patients. So this is the version 1. This is Shaquille O'Neal, the famous basketball player, at Magic Leap recently. The company can create an augmented world, this entire world that's new, in addition to your normal world. I can still see you, you can still see me, but in the glasses they can put whatever they want. And it's going to be used for the gaming industry, so the very fanciful kinds of images about what can be created. But boy, what an opportunity for the blind to be able to provide visual input wherever they have it. So let me tell you just a little more about that. Most patients who are blind, even legally blind, still have some residual vision. With the Magic Leap device, we can capture vision and place it into the residual seeing areas. Without the implant, we don't need the prosthesis to do that. We can take advantage of whatever vision a patient has non-invasively with a technology that has already been developed. It just has to be customized for blind patients. This is a huge benefit, so our first goal is to begin to use that device in visually impaired patients without the prosthesis. But this device will be the front end for our prosthetic system. Both are going to happen. Now, the last sort of strategic opportunity that our group provides is the following. I mentioned earlier that you can place devices on the retina, but you cannot treat patients with glaucoma or diabetic retinopathy or traumatic optic neuropathy because you need to have an intact optic nerve to bring the information to the brain. So what we have done is to leverage our technology to interface at 2 other locations in the brain. The first is the lateral geniculate nucleus. We're the only group in the world doing this. The same technology we've modified to work at the lateral geniculate. Now I said past tense. I should say we are redeveloping the electrode array to be able to insert deeply into the brain. I'll show you a picture in just a moment. This surgery, interestingly, which might sound fearful to you, is much easier than the eye surgery because we are taking advantage of the field of functional electrical stimulation that's been developed to treat Parkinson's and chronic pain disorders and movement disorders. That field's well developed. So a small opening is made in the skull under anesthesia, and then the patients are awakened. The electrodes are inserted with a robot under magnetic resonance guidance. The patients are awake to let the researchers know where the electrodes are, what's being stimulated. They can feel it or see it or hear it, right? And at one sitting, you put electrodes in both sides of the brain. If you put an electrode in the lateral geniculate compared to a single eye, you will be delivering visual information homonymously to both eyes at the same time. If you did bilateral implants, you'd have homonymous bilateral visual input. So this work on the lateral geniculate has to be credited to John Pizarris, who's a PhD neuroscientist at Harvard, and we've been collaborating with him for a long time. But this was John's original idea. He's published a wonderful paper years ago in stimulating the lateral geniculate of a monkey and demonstrating that the monkey can use the visual information. My team is providing the engineering support for that project, and the front end of it will be Magic Leap. But we're also working at the level of the visual cortex. Why? This is our concept for what a device might look like on the visual cortex. So it turns out that at MIT, where we've had this program for 30 years, they had already developed extraordinary microelectrode technology for scientific experiments. So this one shaft has 2,000 electrodes. Each electrode is on the order of the size of a single neuron. Stunning. They have used this in awake animals and recorded from thousands of neurons simultaneously. Now, their goal is to try to understand how the brain thinks. To do that, you need large population recordings in awake, non-anesthetized animals who are doing complicated tasks. So I was just there a couple of 4 weeks ago or 6 weeks ago, watching a rat with a small opening in the skull with a glass covering. On the computer screen were thousands of neurons actively being recorded while the rat was moving a ball to follow an image on a screen that he was looking at. Just sitting there following the moving ball on the screen while the neurons were being recorded in real time. It is stunning work. So my role here is to try to take advantage of that technology to help humans. So here you can see that if you can make one shaft like this, it becomes really easy to make a two-dimensional device or a three-dimensional device. Here you can see from one such device, each line in every different color represents neurons that are being recorded simultaneously in awake animals. So the concept that we have is to use these shafts that would be mounted onto a common substrate that you would implant on the surface of the cortex, and there'd be complete wireless communication into and out of the brain. And if you can make one such module like this, it becomes possible, you see, to scale up the system. You could have, like I showed that picture, you could have multiple modules that are implanted into the visual cortex through which you communicate wirelessly. And those three projects, the retinal project, the lateral genicular project, and the cortical project, would all benefit from the same front-end Magic Leap device. So on the one hand, it may seem too diffuse to be doing each one of these. The reason to do it is that there are many forms of blindness, and you have to be able to interface at different locations in the visual system to help neural blindness of all types. The second reason to do it is that we're doing it mostly by leveraging technology that we've already developed. And the third is that each one needs a front-end device, but we would use the same front-end device for any of those projects. So I'll summarize by saying that my mission in my career has been to restore vision to the blind. My approach has been to leverage technology and to develop assistive technologies based upon those devices. The devices make a potential to help blind patients, but also the same technology has a tremendous opportunity for neuroscience to try to understand how the brain thinks. So here we are 30 years into what might be called the modern era of visual prosthetics, and I believe that the field is at an inflection point. I think in the next 5 or 10 years, the outcomes are going to be substantially better because the technology is simply better. And what do I tell patients at this point? First is that there's hope. Secondly, that it's not ready now. That's the last thing you want to do is give unreasonable expectations to a blind patient. I think there's a lot that we can do with assistive technologies, and here I think the Magic Leap device without the implant is really going to play a role. I think we are going to be able to help just with that. But ultimately, I think we will also be able to create vision with the prosthetics. I have a large team of people to thank. Of course, you understand that I did not do most of this work. It's a large team based primarily at Harvard and MIT, but also at Cornell, Carnegie Mellon, Boston University, and the University of Texas at Dallas, and of course the funding sources. I'd be happy to answer any questions if there's an opportunity to do so. Thank you very, very much.
Thank you very much, Joe. I think this was very comprehensive. As you know, there are many modes of treatment for retinitis pigmentosa, from the genetics to the dietary supplementation. That's what we do at King Faisal, of course, to the growth factors, to the enzymes, to the agents. and most important, the prosthesis, which you talked about. And this is really where the King Khalid Eye Specialist Hospital takes the leading in the prosthesis. So I open the floor for any questions to Dr. Arizo.
And I have plenty of questions, but maybe right now what comes to mind is you talked about retinal remodeling, and that's been a hurdle even in subretinal gene therapy.
Yes.
The remodeling of the retina that may be a hurdle to get the vision as we want. So is there a time frame? Is there a time frame to install these prostheses before the remodeling happens?
Boy, that's a very insightful question. Yes, there is, at least in a broad sense. The answer may not be so favorable. So what Robert Mark recognized was that the remodeling really accelerated when the cones began to degenerate. So you can have wide field loss of rods without a lot of remodeling. But once you begin to lose cones, that's when it really happens. So ideally, you'd like to intervene before patients lose cones. And the problem there from a regulatory standpoint is that those are going to be patients who still have good central acuity. So we were talking a little while ago, the field is going to have to evolve such that the regulatory agencies become more comfortable with implants in patients with better vision. That's going to take time. But that, from a biological standpoint, that would be the time to do it. Let me just answer. The other reason we're working at the lateral geniculate and the visual cortex is just for this reason. Because if ultimately the biology limits what we can do, then we'll have another approach.
Yes.
One more, yeah.
Yeah. There, in the subretinal gene therapy studies, one way to measure the function of the retina as a whole and the perception of light is to do the full field stimulation test.
Yes.
Has this been done in patients with prostheses? Is there a better perception of light?
Full field electrical stimulation has been done to try to pre-select which patients may have more intact neural pathways. So it's used as particularly by the German group, as a strategy to look for intactness of the retina. So you're saying after implantation, is there a way to use full field stimulation?
Because that's been done in patients, for instance, in this RPE65
Yes.
subretinal gene therapy. So they've measured many
Negative potentials. Yeah.
tests for improving vision besides visual acuity, because not
Yes.
everybody improved the visual
Yes.
acuity. Most patients had improved navigation, and there were more than half of them had an improved in their full field stimulation.
Oh, I see what you're saying. Yeah.
So is that going to happen?
Well, that's
with
a good question.
prostheses?
I don't know, and it's a little complicated because it turns out, as you well know, if you operate in the subretinal space, even sham surgery, you can create a trophic effect to photoreceptors. So that's been demonstrated almost more than 20 years ago. For whatever reason, the cells survive better and longer, even if you do a sham surgery in the subretinal space. There are neurotrophic factors that become released. So it complicates it. And from a prosthesis, one of the challenges is that the electrode array actually is relatively small compared to the area of the retina. So that's a challenge, because if you do any kind of full field stimulation, you're only going to be capturing a very small area of response from a prosthesis. Unlike with genetic therapies, you insert in the subretinal space, and it spreads, particularly in the last few years, it spreads pretty broadly. So I think it is a more utilizable technique for genetics. Probably wouldn't be as good for us.
But what are the parameters to know that this prosthesis works?
Yeah.
Until we try it.
Yeah, until you tried, you won't know. But each company, Second Sight and Retina Implant, they've all developed strategies for testing. And I should have mentioned, but I didn't. Because each company was developing a different approach to testing, it's become impossible to compare results. So about 4 years ago, Lauren Ayton, who had been in Australia, who now works with me, we developed an international consensus for psychophysical testing methods for any field of retinal research, whether it's prosthetics, stem cell, genetics. We all have the same problem. Severe vision, how do you measure people who are severely blind? So those, we got more than 100 people to participate in 7 working groups, and our recommendations are going to be posted online probably mid to late summer. I'll be happy to send you that information. But anyway, so we have detailed recommendations about testing methodologies. Yeah, thank you. Yeah,
Thank you, Dr. Rosso, for this really.
thank you.
I think the difference between your implant and Argosto is that that is pre-retinal and the other one is subretinal.
Yes.
I think this is makes sense, to go with that. But the good thing is that for people who's lost their visions either in a trauma or the people who doesn't have an existing viable retinal photoreceptors, which is the challenging for the futures. How we can go with multiple high-tech, technology to help going through the implant in the occipital lobes or fetal
Yes.
cortex, or using the residual optic nerve. I think this is the challenge, and I think what you are doing is seeing that having some bright future, but
Thank
need
you.
to be go on and on.
Thank you very much. I appreciate that. Be happy to take other questions. Yeah. Yes, please. You need a microphone, I think. Yeah, or speak loudly. There we go. Thank you. Great to meet you. Yeah. Yes.
Yeah, thank you very much for this. I think it gives us very great hope to the future.
Thank
But
you.
my question regarding the patient who is amblyopic, those who are severely blind since early on in their life. So is there any hope for such category of patient? Or
Yeah, that's a really good question, and I should have said this, but the use of a prosthetic is predicated upon having had a normal visual pathway early in life. Yeah. So if a person has been congenitally blind, we know that the visual pathways don't form properly. But there's an interesting detail in this. Maybe 15 years ago, two colleagues of mine at Harvard published a paper. I forget whether it's Nature or Science. I think it was Nature. The front cover was a functional magnetic resonance image showing the visual cortices very bright, right? Not unexpected. That's where we see. Well, it turned out this was a patient who was congenitally blind, who was reading Braille. In other words, the geometric patterns of letters stimulated the visual cortex. And that unleashed a new understanding about the brain. So we have auditory cortex, visual cortex. They're actually not different. They function differently only because they get different information. So the point is, we know from Gronker Sewer's work at MIT, the person who's making these electrodes and using them in animals, many years ago he did this experiment where he deafferented the auditory cortex of animals. And it became visual cortex, and vice versa. So it turns out that it's plausible. I'm not saying it could happen. It's plausible that even if someone's congenitally blind and the pathway from the eye to the lateral geniculate didn't form properly, it is plausible that if you stimulate at the lateral geniculate and provide input to the visual cortex, that it could assume a visual role. But we don't know that. That is so far down the line, I don't know, but I think conceptually, the idea that these visual cortical areas change and can adapt over time provides hope to us.
If I can just add to that, we know with the Leber's congenital amaurosis, when they did their genetic, if you will, treatment, a lot responded, and if you treated the Leber's congenital amaurosis, as it mentioned, they're blind from practically infancy. So they did respond, so there has to be a reason. If we had left them, we know that when they're from the beginning and since infancy, they don't see. They haven't been able to see, but we can't, the treatment was given, and long and behold, they were able to walk. They were able to navigate much better than what they were. So in answer to your question, we do have something in realization. We have just time for one more question, if it's pending. Please.
Thank you for your lecture. I have a question about implanting them in the subretinal space. As you can see in the photo, they reach up to the ganglion cell layer.
Yes.
Is there any residual thickness of the retina to implant it, and have been there any electrode that go full thickness, that penetrate the whole retina?
So we've made multiple heights to make a judgment for which one we like the best. And of course, the heights are going to be a little different for humans. This was a pig. So there's a legitimate question about where should we interface? I mean, maybe the outer plexiform layer is better than the inner plexiform layer. We don't know that. So in the device that we are testing for the FDA, it's a hybrid device that has two different height electrodes. One sits in the outer plexiform layer and one sits in the inner plexiform layer. We did not want to go taller because you then risk the possibility of going through the inner retinal surface. So it turns out that in patients with end-stage retinitis pigmentosa, there's almost a 30% variation in the thickness of the retina. So we wanted to have a tallest electrode array that would still be acceptable even for the most severely affected patient. So.
Well, thank you very much, Dr. Rizzo, for a very comprehensive lecture. You have honestly enlightened us, and what better than to start at the King Khalid Eye Specialist Hospital, which is the leading hospital with all the different, and it's actually been broadcasted, as you saw, the young gentleman, to the urban areas. So thank you very much.
Thank you. I appreciate it. Thank you so much for arranging. This is great. Thank you.